Normally, if you have a periodic structure, you send in light, you have Bragg diffraction. But as soon as the separation, and it shows there, becomes less than the wavelengths, and you see there, the only order that survives is the direct light going through and being diffracted by the structure. The approach of Fermi is always one, the most direct and simple way to arrive at an explanation. Completely uninterested in complication. Simplicity and directness. So that, in a sense, influenced me. The undergraduate, sometimes I've heard, particularly from female students, well, I'm not capable, I'm not intelligent enough, and I just say nonsense. I mean, look, I fell in love with physics 6 years old. Did I build motors? Never. Was I good with my hands? Not particularly. Was it I had a talent for science? No. But I loved so much to read about whatever I could read. When I was ready to go, I said, I'm going to be a physicist, and I decided when I was 6 years old. And that's purely passion.
This week, Xinghui and Misha speak with Harvard physicist Federico Capasso, a pioneer of metasurfaces and metalenses whose work has transformed modern optics. Capasso walks us through metasurfaces, generalized Snell's law, and how academia and industry can work together to turn fundamental physics into real-world technology. Please welcome Federico Capasso.
So Federico, we have already met with you previously, and we talked a lot about Bell Labs and the invention of the quantum cascade laser. So in this episode, we would like to shift the gears towards the more recent inventions of the metasurfaces, meta-optics, which is more like related to your when you are a professor at Harvard University. But could we transition from the times when you were ending your activities like at Bell Labs and then coming to Harvard?
Yeah, in fact, it's an interesting question. In fact, the transition to really from QCL to metasurfaces was triggered, and I actually mentioned in an interview that I did with ACS Photonics some time ago, was triggered by a question that a great colleague who I was collaborating with, Professor Jim Anderson, he's a leading atmospheric chemist. He's one of the guys that basically engineer the famous Montreal protocol for the control of the ozone hole. So he was sending quantum cascade laser in not only in high altitude places, but he wanted to put into actually drones. Why drones? Because drones can fly low, close to the surface, and he was interested, exciting problem, in measuring the plumes of methane, because the permafrost has literally inside 40 teratons of methane, which is the strongest of the greenhouse gases, okay? And there is a concern that with global warming, could be even a sudden release of methane. And over time, over the years, he has been sending, these crazy pilots on planes go very low, but he said, I want to go even lower, measuring the plume. I want to measure the stuff. And so I need a drone. I need a QCL in a drone without a lens. And that was really a very interesting question. So I said, I don't know how to do it. I think it's crazy because the divergence is so large, How can it be collimated? But then I remember in this office with a student of mine, Nanfang Yu, who is a professor at Columbia now, we huddled together and we said, that's it. We are going to make a collimator, if you like, a collimating lens with metal, with plasmonic, because in the actual mid-IR, there are no losses, basically, very little losses. And we did it, okay? We transformed the beam from a divergence of 60 degrees this way and 30 this way to just a few degrees, almost a circular cross-section beam. Okay, so that was quite exciting. That's how I started to think about. Then for a while it lay dormant. Incidentally, we wrote a proposal. It wasn't funded, but that's kind of typical. When you're a professor, you get used to stuff. You just keep on writing them until eventually something gets funded. Okay, that's been always my philosophy. But then that at some point lay dormant. But then one day I said, that's it. Now we can make a flat lenses stand alone. We don't have to put them on the actual facet. So this was the beginning for us, how essentially my group got into Metasurface it didn't happen overnight, because we published that paper and then we waited for 2 years, and then that paper there came, and we actually were thinking more about, what if we put sub-wavelengths really structured together, we can really engineer the phase, the wavefront, okay? Now, of course, and we realize quite immediately this would be much more effective than SLMs. SLMs are limited. SLMs can hardly control the polarization, whereas with this stuff, you can engineer the actual polarization. And this, I think, is actually the greatest impact. Of course, metalenses are now, there are 100 millions of meta surfaces that are commercially available now. I started a company, Metalens, and the Metalens is made by Metalens. They're actually made by
at the end.
by foundries.
Yeah,
By foundries, using some exactly right. I mean, they are in two different cell phones and other stuff. Unfortunately, I cannot tell you which, but everyone knows.
We'll ask Rob for that.
We'll ask Rob.
Next episode.
If you go, you know what I mean. But so that's how that transition happened. Okay, in a real sense. So it's always a clever question. Often can trigger something, right? So.
And that was actually my very first job. I did technology transfer, and one of the projects I had was to commercialize the plasmonic collimator with Philips. Yeah.
Really?
Yes. I was talking a lot with Nanfang back then.
Then it didn't go really anywhere commercially.
Because Philips uses surface emitters, and then
exactly
you don't have the as large.
So plasmonics
angle,
at the end, was fun. We got this in this paper in front. It was implemented, if you like.
This one, the 2011, right?
It was actually with plasmonics, although it's much more general. The mathematics behind it applies to the electric metasurface. I mean, but the plasmonic stuff eventually, plasmonics has been oversold over the years, not by us, I must say, as the bridge between. It's important to state it, between electronics and photonics. This is simply an invention by academics, because academics, professors, are often self-referential. They start to say something is important, a bandwagon gets created, other professor, and sure enough, now this field builds up. Now, but often it's just pewters. And this was largely what happened in plasmonics. But there was a few very interesting stuff that we did with Naomi Halas, this cluster of plasmonics things where we found some very interesting states,
Jonathan Fan's work.
Yes, exactly right,
Well, from scientific point of view, I believe there were some demonstrations of ultra-fast modulation.
Yeah, but at the end, didn't make an impact.
Wasn't commercialized.
Yeah, it's more like a
yes.
demo.
Yeah.
But for instance, with the collimator, that was one of the first things that then Rob with Metalens did with Trump.
Exactly
so
right.
The concept works.
I would say the collimator was an interesting bridge towards stuff with the electrics and then metalenses, right? Mm-hmm. See, we have to be pretty tough, when we make claims. The claims can be made either for a scientific invention, a breakthrough, right? And it's about the basic science. And I would take it that paper is more basic science, you know what I mean? But then if we claim a device, the judge, the only thing, is it going to make it in the real world, yes or no? If it's no, then it can still have an impact, because it triggers more ideas by other people. So that's good, right? But the ultimate thing is it becoming real in the real world? And that is, about, only when I was at Bellas, I looked it over. It's less, then it was sort of less than 10% of the invention. A few percent would really make it, right?
Mm-hmm. Do you want to briefly explain to our listeners the significance of the generalized Snell's law?
Well, basically what we realized there is the following, that with metasurfaces, you can, well, let's see, maybe we can show a slide here. The important thing about the metasurface is this, I mean, and this is something that is an enormous confusion around, okay? What's the difference between them? It is a periodic structure, right? What is the difference between metasurfaces where the periodicity is typically subwavelength, right? Quite a bit subwavelength, and a periodic structure that is more like a crystal, you know, like a dielectric crystal, right? And that picture shows it. Basically, as soon as normally if you have a periodic structure, you send in light, you have Bragg diffraction. You have Bragg orders that corresponds to the Bragg condition being fulfilled, basically, right? So it behaves kind of like a crystal. But as soon as the separation, and it shows there, becomes less than the wavelengths, and you see there, okay, the only order that survives is the direct light going through and being diffracted by the structure, right? This is the essential thing. Now, you'll be surprised the ignorance of this and the confusion. You know, I hate confusion, as she knows, you know. I'm obsessed by clarity, and this is the key thing. That's why when I give a talk, I always make this point.
I love this demo.
Yes, this is great. This is a very good.
You see, right? Exactly right. Yes. That's all, right? So what we realized here, we had to go significantly sub-wavelengths. This is one reason why we chose the mid-infrared, right? Because it's easy to make it 100 nanometer separation when you have a wavelength that it's 8, that's really, you are in the metamaterial limit, right? So you don't have, so you only have, so now since the orders of diffraction, like in a crystal, disappear, and they disappear rigorously, okay, now, however, I can phase the surface in various ways. One, I can have a constant phase. If it's a constant phase, light simply goes straight as it goes there, right? But if now I put a phase profile, right, a phase profile, essentially every point of the incident wavefront gets shifted differently when it hits the actual metasurface. So this point here, it will have a phase shift in distance unit, the next will be greater, and so forth. And you can engineer to have a linear phase ramp. And people have called these gradient metasurfaces, okay? Now you can rewrite the equations for the angles of reflection and diffraction, right? And you find they satisfy a generalized Snell law, okay? The Snell law typically, you know, it says the sine of the angle of incidence divided by the sines of the angle of refraction is basically equal to the
we should use that
to the ratio
illustration here
to the ratio of the refractive indices. Okay, now when you have a phase gradient, okay, there is an additional term, okay, which is intuitively obvious because the angle of deflection now will depend. And it depends on how you design the phase gradient, but we are talking here of a linear phase, so a constant phase gradient, so it will be diffracted more or less depending on the steepness of this phase, right? And that's what and this kind of caught the imagination of people. I was never, I was suspected. This is the most cited paper I've co-authored. You know, it has more than 10,000 citation. I think actually, you know, I'll tell you something is, what did I contribute in this paper? My group had done the simulation, the experiment, but what I didn't like, there wasn't a simple thing. So one day it hit me, Fermat's principle. We have to apply to this. And in 2 lines, we get this equation. And the editor of Science told me once, he said, he always points to this paper as a good, and I'm very proud of it, I must say. It's okay to be proud once in a while, right? He said, because in the first part, everything is explained very simply. Everyone understands. Even a high school student can understand it. And I always point it out as a way to actually write. So, and that I think is part of the reason why it was cited so much. I mean,
was this Shalive? Was he back then?
No, Shalive then arrived closely, but was a bit late. Okay,
because you worked with Shalive.
No, I know.
Because I know when we received
but no.
You received this for review?
Yeah.
Yes, but then he was honest. Okay, what he did an application of deflection at visible wavelengths and cited very clearly this paper. Okay, so it's okay. You know, I mean, this is part of the scientific process. You know.
You were in Shalive group.
Yeah, I was at that meeting. Where I was like, "Wow, this is great. Let's do it."
Yeah, I remember that.
And then I remember Fermat. I remember his portrait because after this paper, Shinji Nio was the one who was taking care of the metasurface kind of direction, and in all his presentations, he would mention that Fermat principle for how it used for metal.
So you're the origin of that narrative.
Well, you know, Fermat was incredible. You know, it's the first example in physics of a use of a variational principle. The Maxwell equation had not been invented yet, but the beauty is variational principle sit above the equations of physics. Like, you know, you can, there is a famous example. Well, for example, you can derive the equation, the field equation for general relativity from an action, from a variational principle. And this was done by David Hilbert, in fact. He wrote down the equation, you know, for the action. And from that, it's very simple to derive. You just use the Lagrange equation, basically, right? Variational principle, right? You can write down the equations of motions. Okay.
And then I actually remember there was like Andrew Weiner, who already unfortunately passed away, but he would like torture Shinji. He was like, "Why is it like? What about blaze grading? Like, isn't it just?"
I know exactly what it is, you know. But this is people do not appreciate the technology side.
Yes.
I mean, it is very true. I mean, if I have a blaze grating, exactly the blaze grating essentially allows you from a periodic structure to go just in one diffraction order. Which incidentally, you know how it works, is the one where the beams are actually perpendicular to the facet. That's the preferred directions, right? So absolutely. I mean, the key is that this, if you like, is, I think the honest way to say that this achieves the functionality of a blaze grating, but it opens up a much more general way to think about it, right? The fact that you can engineer the phase, you see, with this is what I've had arguments with people that say, how about ordinary diffraction optics? I say, sure, diffraction optics can do in principle all of this, but it becomes so damn complicated. Why is it that only with metasurfaces people have started to really talk about engineering the wavefront in a complex way, right? Because of you can do it if you think in terms of engineering the diffraction orders in this way. It's a much more general way to actually present it. You see what I mean? With blaze grading, you're just stuck there. What else became after the blaze grading? Tell me what came. Not much.
So you don't have degrees of freedom to shape.
Exactly right. It's the degrees of freedom to shape. This is really, I think, what Metasurface has done. The degrees of freedom, the fundamental physics behind, let's not kid ourselves. It's obviously the same. I mean, after all, once a guy gave me a hard time in Singapore, and I said,
I know which guy.
And you know who he was, right? Your friend, right? And I said, sure, everything we are doing is contained in Maxwell's equation. And there was a big laughter. He didn't like me after that because basically I wanted essentially to ridicule him a bit because you know what I mean. You have to understand is what you said. This opens up a way to engineer to engineer the wavefront in ways that you cannot do with the standard technology of diffractive optics and so forth. Or if it can be done, it's such a technologically hard that people just don't do it. Because at the end, technology impact means you got to make devices and sell them. If it's so hard, why bother? That's why a lot of the initial diffractive optics has sort of, it's there, but it's not going, it's not had this runway like metasurfaces, right?
Yeah, and just for context, like the most famous diffractive optic is like from lighthouses, the Fresnel lenses. So I get that question all the time, like what's different to Fresnel lenses? But actually even the optical quality is different because you don't have the shadowing from like the
absolutely
exact point.
right.
You don't have the glare, the halo effect.
The halo effects, all this stuff there, because we don't have this indentation and so forth. Then people counteract and say, but then there is the so-called this digital diffractive optics, you know, that to some extent, you know, eliminates some of these. But again, it's the complication. I mean, people are not going to put a lens in cell phones with these methods, whereas now this stuff, guys, is in cell phones.
It's multi-level lithography. It's really difficult. Yes.
Right.
So I guess like both Xinhui and myself, I have like experienced so much of resistance from the diffractive optics community.
Yes.
Like even for my papers, they're like, "Oh, this is like, where's the novelty? It has been done like in 80s," and then I would have to kind of prove. But for yourself, you were like you were like the pioneer in this field. How did you go through the resistance?
It doesn't bother me at all.
Oh,
I had learned early on, you know, when I was at Bell Labs, you know, quoting a say from the actual Bible, it says, you know, knock off the powder from your shoes. You know, it says something that Jesus says at some point. You know, I said, this is just, most of it,
Dust.
Some of it is honest question. Some of it is just people that, you know, can't accept the fact that there is, you know, it's a new way, if you like, it's a new way of doing diffractive optics, but the fundamentals are the same, right? Although, I mean, you see that simulation there came after the metasurfaces were born, okay? It's a very nice website, you know what I mean? This stuff was not available in books.
Yes.
Before this paper, they're there. That's what I'm trying to say.
Yes, and
in fact, the guy who has really looked at it and he's a Russian scientist in Denmark, Bolshevolny. He's a great guy, very deep thinker.
Yes.
He's the guy that has basically given the best answer to these questions, better than me even.
I remember,
but basically, you gave it before, right?
And I also remember, like, when we were writing patents, they would ask us, like, define what a metasurface is, and we were like, every group kind of has their own definitions. So even at that point,
but the main part is, let me say, it's actually the polarization part. In the polarization, you know, basically, you see, what we have started with student Noah Rubin, who is
cool network as well.
The cat dog.
Oh, the cat dog?
No, it's before that is the matrix Fourier optics.
Oh yeah, this one.
Yeah, this matrix Fourier optics here. We realized there, you see, that it's another. In fact, we went when we were having the first ideas. We went to. I said, you know, no, we are going to go to meet the father of Fourier optics, Joe Goodman, to tell him here, does he thinks that this is of value, what we wanted to do? And he said, absolutely, encouraged us a lot. He says, I've never thought of it, because his is a scalar theory, you see, and that's the novel part, okay? In scalar means that you write the far field as essentially a plane wave expansion. That's how it's called. So it's a Fourier series, okay, where you have the plane waves, and in front there are coefficients. But the coefficients, they are scalar, because it is a scalar theory. There is no account of polarization in ordinary Fourier optics. we realized here, and others realized, that we could do a tremendous control of polarization. In fact, an early paper was by an early student, Balthasar Müller, who now decided to make money for quite a few years. I know him very well. It's fine. I mean,
I will send him the clip.
he's a bit lost for science, I'm afraid.
He's a brilliant scientist.
Very, very brilliant.
Yeah.
And that showed, for example, that you could use polarizations, okay, in very interesting way, okay, to control holograms. You had metasurfaces is one polarization. You had a cat in the far field. The opposite circular polarization, you had a dog, okay, and that showed the beginning they gave us, and then came my new student Noah Rubin, and that's a very powerful generalization. Now we can generalize, right, metasurfaces, for which we can calculate rigorously with this matrix Fourier optics. You see now what is the difference. There is still a Fourier series of plane waves, but the coefficients now are matrices. Okay, in particular, they are Fourier transform of the Jones matrix that describes the actual metasurface. Okay, very simply, because if you hit an anisotropic structure with a polarization this way, you're going to get a different far field response than if you hit it the other way, right? Which means then that the coefficient in front of the plane wave must contain this information on the polarization, on the different polarization response. And it is mimicking what scalar Fourier optic does. It is you have the Fourier transform, the coefficient are the Fourier transform of the Jones matrix of the metasurface. And that is amazing what one can do. You can do this Jones matrix holography where you can design the far field so that depending on polarization that is incident, different parts of the far fields light up, right? So you can make, holographic movies if you want to. You know what I mean? It really opens a lot of stuff there. And this stuff now is entering in cell phones. That's the next big thing, okay? You look in Metalenses, the company I started with Rob Devlin. Among the products in the next 2 years, there's going to be this Polar ID, face recognition, using essentially a camera that is conceptually our camera, okay, that sort of can see polarization. Our faces is how it appears. If you look with polarized light, it will look differently, right? So that means that if you try to enter into a cell phone with an actual fake, either reflect things for sure, but also an actual mask, it doesn't work, okay? And this is basically 100% foolproof. This is a huge breakthrough. And an example of this is another example of polarization optics that has is going to make a big impact, you know.
Rob had an interesting demonstration where he made a mask of his own face, and it doesn't work, but then with his real face. But the mask looks just like his face.
Did he also hack like the current?
The current
ID. How's called like
Polar
face ID with like whatever is built in.
I did not see that part, but I would imagine.
No, it's there. I mean,
it's there.
Yes, because you can do that like on a regular face ID.
In fact,
you can fake it.
For the demo.
In fact, now it's used in China for kiosks. You know, when you want to buy something, you know, and in order to open it, of course, they have to verify your ID because you have to actually pay, right?
Well, even in the US now, in the Whole
right.
Foods, like there is a store, like you just come in, it scans.
Yeah.
I forgot its face or something else. You just pick up the stuff and you don't have to pay for it.
It's the point is something that works, you know. I mean, you know, the reason the iPhone is so popular also, it's a very secure technology, okay? But there is one step further, okay? If you look at transactions in the future that are really large, the kind of security you have with the iPhone is not enough. You need the polarization. I mean, Rob can tell you the full story. I mean,
We actually, it would have been fun to have him here as well.
it's very exciting. I mean,
We'll have another one with
So
Rob.
another
Yes.
episode.
so I think,
Yes.
look, ultimately what I tell people is also, because, I always said, and I'm proud of it, always one foot in the science and one in the technology. That's the area where I know I'm really strong. And so sometimes I get impatient with people who says, do you understand that the fact that the foundries can make this stuff using the same technology they make ICs, it's revolutionary. And they look at me, it's revolutionary, right? Because you now have, it's easy to make and you can make millions of them. That's why now there are 100 million metasurface. In fact, UMC now is the foundry, making the actual metalenses. And that is huge. And that has been enabled by this metasurface technology. And people that would say that was obvious from all their diffractive optics, I'm sorry, they don't know what they're talking about. I mean, why none of this came? Why this impact didn't come from ordinary diffractive optics, right?
So was it the background from Bell Labs help you, or did you?
Yeah, well, I mean, here now we go into the maybe some interesting things for me to discuss. I think the education that I had, there was one strength. A lot of people in Europe criticize, the academic training, and they have some valid thing, but there is some good thing. The good thing is the breadth of the education of the graduate courses. They're really very, I mean, we did, anything from semiconductor physics, general relativity, nonlinear optics. The courses were very hard. The failure rate was this. It's a system that now it's changing, even in Italy. For the better, I'm not so sure. I think so. I think having a broad education, and I always tell the student it's important to have a broad outlook, because at the end, I mean, science, the principle of physics apply to any area of physics, right? So we have to ask now, why is it so difficult for people, often, not always, to move from one area to the other? Because they were not educated properly, right? Yeah. I mean, the breadth comes from the very nature of science, right? The principles, particularly in physics, are well known, so it should be possible to apply them. But often these things are taught in a two-things way. They're taught, the principles are taught as if they apply only to optics. At least the impression is that way. It lacks the big picture lacks. That's why here in the introduction of that paper, I thought about the stuff of Fermat. I says, this can really be an eye-opener. Is it new? No, it's not new. But that's the whole point. What is new is the fact that someone like me realized that we should use a well-known principle of physics in this particular area. And so it can be done in many areas, right? So going to Bell Labs, of course, was a fantastic place, because there was this, people in research were not restricted. They were hired, they were given some space, some good money, and then they had to we couldn't work on anything. You couldn't work on high-energy physics, but
Why?
condensed matter, optics, photonics, and then people could really roam around, you know what I mean? And then there was the intellectual atmosphere, the constant excitement, right? Tons of seminar, many smart people, right? So that are all the ingredients, right, for innovation. And then not separating the science from the technology, which typically this happens in academia far more than companies. Companies have to make things work. Right, so for them, physics is an actual tool.
Yes.
Right, and it's pretty impressive, the research. That's why I tell the students, look at what industry does. Like we have some great collaborations, with the top companies, Samsung, KLA, and now soon, hopefully, with Meta. Corning has been going on for 5 years. In fact, it's a great collaboration. They're using metasurfaces to make devices that can be potentially useful for the next generation of communication systems, right? For example, mode couplers, to couple in the modes of a multimode fiber using metasurfaces, So we published some, and that work applied? No, it is hybrid. See, I just can't stand. One of the things that makes me really angry when people makes this distinction, because they are not useful, right? And that's not how things work in the real thing. Is that, people often, I'm telling you, are kind of, there is an attitude, I remember for a while, now it's changing, fortunately also at Harvard, that physics department did not want to hear application. They put it down, right? And often it's an insecurity. They are afraid if we are invaded by engineers, we can't do physics anymore. Nonsense. Nonsense, I mean.
This is particularly a problem in Germany. Yeah.
Yes,
This
right.
is very.
But I think it's like almost everywhere. This engineering, physics.
It's not pure anymore. It needs to be kept
point,
pure.
the Bellhouse was
and
a
then,
fantastic
yeah.
place, because this culture, and this culture, unfortunately, of it's. Desgen wrote a beautiful book called Fragile Objects, and one chapter he rails against the French system, he says, that started with the philosopher Comte, that made a classification of science where mathematics was at the top, then there was physics, chemistry was not even on the actual list. Okay, and that permeated the educational system, whereby essentially not only certain disciplines were put down, ignored, okay, it was also, he says, the disdain of manual work in the actual lab. The top people didn't have hands dirty, right? And he says that, unfortunately, he says, and this culture, I mean, in the United States is much more mixed, right? If you look at electrical.
Yeah, it's a huge difference. Yeah.
Right. But I think, yes, basically, I think my research has been, if you want to look at philosophical point of view, is the combination of the education that I had, which was broad, with some top professors, and then followed by many years at Bell Labs, shaped the way I think as a scientist, right? And I can't escape anymore. Anytime we do something in physics, it comes to me like the Casimir effect, we just wanted to do some real measurements. The cleanest way, the first was with MEMS technology, because then I thought maybe we can make some MEMS gizmo. But then I got fascinated by this famous paper by Dialochinsky, Abrikosov, Dialochinsky, and Pitaevsky. Okay, in fact, Pitaevsky was here to visit us. Okay, and about that occasionally you can make the Casimir force change sign. So I was really fascinated about this. Yeah, I'm fascinated by the bizarre. That
Can you
true.
explain it? Like instead of
yeah, okay.
Towards each other, they would push
It's
away?
very difficult to explain. What you need to have is a dielectric function of the three materials. This plate, and intermediate. We use a liquid because we wanted to see the force between this and this. And if there is a descending or ascending order of the electric function, in fact, it's more complex. A particular type of dielectric function, which is a complex integral like the Kramers-Kronig transform. You can imagine, then the force becomes repulsive. So when Pitaevsky visited here, I asked him, I said, can you explain it? Can you explain it to me in simple terms? I asked actually Dialochinsky first when he retired. There was a symposium. They invited me. I spoke to him. He says, Federico, honestly, I can't explain it in simple physical terms. Then Pitaevsky tried. Now I have to go back to his explanation, but he said it was actually very hard to do this stuff, right? Because you have to, because the Casimir force is interesting, like the van der Waals force. It depends on the dielectric function, but it's the dielectric function at all frequencies, you see. And you have to be careful. You can't, the mistake that some people, including me, made was that I said the ones that matter are the ones that fit the distance between the plates. That's not true. Okay,
like
what matters is,
right?
Exactly right. There's no resonance in the Casimir force. And so there is this integral of all frequencies. And at the end, lo and behold, if there is a certain condition, it becomes a repulsive. I don't think, maybe someone can figure it out, a simple way to explain it, you see. You need to put the properties of material. But the Casimir is a good example. I started to get really excited about it. And at some point I was thinking, maybe we can use the repulsive force to control friction. I even filed a patent, but it was not accepted.
Oh, why? That's
I think that was a mistake,
Yeah.
We had really some ideas, that you could control. Because you see, friction is a very interesting problem. Again, it's a problem if you mention it to well-groomed physicists. They will look down. He says, that's the dirty thing. Dirty. This is one of the most difficult. First of all, it's a QED problem. Okay, friction. Okay, and it's complicated by the fact that the indentation counts, right? So there is some very prominent people that I actually met. The key ones have actually passed. Okay, one was a Russian, Israelivsky, something like this. Okay, and he actually did pioneering work on friction. But I was interested in friction because there must be in any situation an optimum friction, right? Because you need friction for movement, but if it's too much, things don't move. So what's the optimum friction? And this is a question that has not really been studied fundamentally.
Yeah, it's a gecko comes to my mind right away. When we're talking about it.
No, you see van der Waals forces. Okay, that's actually pretty well understood. But so at the end, we couldn't. I was thinking I could use this as a way to reduce friction of fluids flowing in a natural pipe, if I have a descending stuff. But that also then, and then at some point, I kind of lost interest. But, so not everything must lead to a gadget. I mean, that would be nonsense. I mean, if one said, this stuff must lead to a gadget, I would say, wrong. Okay.
But practically, like, is it possible, like, just hypothetically, it would be like some sort of like a coating for the pipes?
That's
like
what we were thinking. We were
Yes.
thinking but it's difficult to find these materials that satisfy this condition. There are not so many. Okay, in fact, I looked at it. There is, it's not, sort of, I lost interest. I mean, but it's an example, I mean, that at least we did some good physics, that's for sure.
But then, like 3 years back, there was one paper by Wilczek who started to be interested in controlling this by using chirality. But
Yes,
that makes it much harder to
I
control.
looked at the
yes.
paper, but it's, in fact, thanks for pointing it out. I looked at that. In fact, they say, they cite our paper and say, in one of the passages, said, but yeah, this effect is small, absolutely true. But this chiral thing is very difficult to achieve in
It would
practice.
be very, very difficult to
It's
achieve.
just a clever,
yes.
it's very clever idea, right, to use chirality.
Like, going?
Well, the most exciting part, I think, is, to actually the so-called dynamic Casimir effect, okay? That if you have parts moving, okay, without charge, okay, because if you have like plates, people calculate, if you have plates, and they start to oscillate, okay, you can excite with vacuum fluctuations, okay, the vacuum fluctuation get modulated. The 0-point fields get modulated by the modulation. And so what you can show is, for example, that if you modulate at omega, you should get out 2 omega. There is a simple argument for 2 omega. Real photons coming out, but it's a tiny effect. It's called dynamic Casimir effect. People have tried for the last 20 years, and so far they found analogs, but not quite the real thing, okay?
And then just going back to metalenses or metasurfaces, the first big paper was that science was the science cover paper with the metalens. Like there could have
2016
been,
or which one?
yeah, I think
Oh,
2015.
yes.
There could have been many
Yeah,
different.
the one
things
is interesting. What's his name?
But even the choice of presenting a lens, that is a choice because you could have shown some other optics. Like, why did you choose? Was that obvious?
The lens is so far. In fact, I knew when I saw the Shalive paper, I said, my people, now the next thing we're going to do the lens, and we have to do it extremely fast because I'm certain that Vlad's people will do that. So we published a nano letter. Okay, a nano letter, okay, on it. It was an inefficient lens. Exactly. It was an inefficient lens, but it proved the point that you could get diffraction limit. In fact, this is also, I think, has thousands of citations, you know. And again, it's sort of this sense that had to be, the lens is fundamental, right? If you can't make a lens, right? In fact, we made a quarter-wave plate, which, it's sort of okay, right?
It will stay in textbooks, right? With this hyperbolic phase profile formulas.
Yes, right. But you see, that's another example, you see. If you actually go back, I'll show you something nice. Okay, this shows, you see, the wavefront, that you can basically arbitrarily shape the wavefront, okay? And the way to explain it intuitively, each element creates its own wavelet, and then the wavefront, at least far enough, you take the envelope of these wavelets, and so at least intuitively you see how the shape, you can arbitrarily shape the thing, right? Now let's go to the next one. Yeah, this is very simple now. How you design the lens. That's the hyperbolic formula, and the way I explain it, you know, and when people make it more complicated, I ask them, why are you complicating showing the simulation where this is the most thing? What you say that all the rays have to arrive in phase at the focal point, right? Which means, but the rays have different propagation phase, right? So you must compensate point by point. If I have these two rays that have to arrive in phase, the metasurface must provide a phase difference so that then the two paths, this one and this one, have the same phase. And that's what it is. You see there, right? That formula there is just the 2 pi over lambda divided by lambda times f is what? The phase shift of the chief array.
So this is Federico's formula.
No, it's not my formula. No, but I'm saying, you see, I'm always irritated by the fact why people, and it seems to me it's a bit of a way people somehow feel it makes it appear more important than it is. But that's wrong. Okay, it's not up to us to judge it's important, but to deliver it in the most, I'll tell you something. I think this is where University of Rome came. 3 of my professors worked with Enrico Fermi. One was Edoardo Maldi, was a legendary physicist. He participated, 21 years old, in the experiment where Fermi proved the radioactivity induced by neutrons. And then the chain reaction came. And he was always telling us in class, often he said, and then we had another one, Persico, who was the theorist of the Rome group. And then I also had some stories from my father-in-law who interacted with Fermi. He says the approach of Fermi is always one, the most direct and simple way to arrive at an explanation, completely uninterested in complication. So both the stuff that is easy to understand, in fact, even his theory of weak interaction, here to explain the beta decay, basically, was done in a very simple way that basically can be understood by even a very good undergraduate student, wherein it's a fundamental paper because he quantized matter fields, right? He says now we can, by analogy with the creation of a photon, he says we can now create particles. So we create creation and operators and distraction operators for particles that have mass, right? That's how modern field theory started, in this simple paper of Fermi. And I remember always this professor kept on pounding on us, says simplicity and directness. So that, in a sense, influenced me, you know, which now it's sort of almost obvious. So I feel terribly irritated. I think people want to make things appear more difficult or more fundamental by introducing unnecessary mathematical complication. Like you can derive that by diffraction theory, right? Simply, right? It's very simple. But if there is a simple way, which is this one, this is more valid. And this is actually rigorous. It's one of the few cases I tell that no modeling is actually needed.
Yes.
Right? Right?
Yeah, that's beautiful. That's beautiful.
Right?
From the Vlad side, I can actually...
From the Vlad side? It's funny because we were sitting in 3 different places around the world observing the same thing happening.
Yeah. So I when I just started the Vlad's group in 2010, there was Satoshi, my colleague, so he worked on plasmonic lenses.
Yes, right.
So essentially it's like a slit, it's a metal film and then making the slit, making it like a flat
like the plasmonic
flat
collimator, like a cylindrical lens. Yeah.
So but then I think they later tried to make it even tunable a little bit, but
right,
it was more like based on...
At the end here, I was really driven by these 2 papers, this Nanoletters and then the one on science, by the technology aspect, you know. That actually I couldn't, if we can make a lens like this, you know, it's a tremendous simplification, right? I mean, you think about it, that if you try to make, I tell people, if you take a simple refractive lens, okay, you have the aberrations kill you. The fact that the rays do not converge on the same point, that's spherical aberration. Okay, now this also eliminates the astigmatism. Okay, if you want to correct coma, you have to do more complicated things. But in general, the control of aberration with meta-optics is much more easy than it is with the regular thing. And this, again, people can tell me, well, this is diffractive optics. Yes, sir, but show me these results. They make it extremely difficult. Fresnel lenses, she said.
Do they also show this like formula for Fresnel?
Honestly, I don't know. I decided not to claim anything on it because I derived this in a very simple way, and I said it's so obvious that probably someone has thought about it, and it's probably somewhere. We couldn't find it, right? But I wouldn't claim that we were the first one. We were certainly probably among the first one to do it with actual metasurfaces, you know, that someone must have tried by other methods possibly, right?
To what extent did you go and look back at radio wave experiments?
That was another question that came, in fact, because when we published this paper, other people that got mad was the phased array people.
Yeah, I see. Phased arrays,
you know what You know what I told them? I told them, look, in phased array, your separation between the elements are not subwavelengths. They are typically wavelengths, and that's the difference, and that's the difference there.
And that brings us to the previous illustration of having a lot of photons and efficiency.
It's a beautiful illustration like that one.
Yes, yes. That makes it very clear.
But you know, you'll be surprised. My obsession with clarity and simplicity, that initially I thought, I'm the slow one, so if I can't, and which is true, if I can't find a simple way to explain this, but then over the years I said, I'm not the only one confused, okay? Most of the practitioners are actually confused, or they understand the thing primarily just mathematically.
Yes.
And they are not able to provide a physical explanation. You know what I mean? And it's always a problem. I mean, I think, of course, sometimes, the mathematical solution is just the way to go for complicated enough problems, right?
Yeah, where we don't have good physical intuition.
Yeah.
But actually, V.I. Arnold, the author of Analytical Mechanics, he wrote a funny essay about that, where he's mostly complaining about the French education system that's relying on.
Arnold?
Yes, he did. He did a lot of
the
physics.
Analytical Mechanics.
It's the Analytical Mechanics guy. I will send it to you. It's
it's
a funny
interesting.
read. Yeah.
Yeah. I mean, it becomes kind of a vice,
So do you think if you wouldn't write this paper, could like AI now try to write this formula?
Oh, sure. I mean,
It's not.
But I mean, I think AI, I'm a fan of AI, I use it in the most obvious way, See, AI is very, I think my feeling is this. AI, see, once I started for fun, I said, it's not in the quantitative things, of course. I mean, what is extraordinary is what Jumper and the other one that got the Nobel Prize in chemistry, they were able to predict the folding of 200 million proteins. That's extraordinary. That speaks for itself.
Yeah.
Right? I mean,
A lot of
but
work.
but the other areas are the areas in the actual art. Like, for example, for fun, I started to ask ChatGPT, please write me a poem in the style of the English poet Yeats, And he wrote something, and then Tagore, famous Indian guy.
Yes, very
And then
good,
you
yeah.
give it some themes. I'm telling you, what comes out is very good poetry. So I think in the area in the creative arts, AI can have a lot of look. But I mean, no one really understands how. ChatGPT. There is a beautiful little book by Steve Wolfram, who is not known as being a modest person, right? And he explains. Talks about ChatGPT. It's very well done. At some point, he said, the way people think it's done, is you start with a natural word, it looks for the next most probable word, and so forth. He said, but that's not how it works. The way it works is there is once in a while it goes into the third most probable, and so with these procedures, you get a creative thing. He says, we have made absolutely no progress in a model, in understand, again, what I call in this case is a sort of physical model, How does it work? And now this is the other savory subject, diverging a bit, I mean, research is a complex system. We all agree, right? I mean, the ingredients are obvious. You need a good leader, right? And there are different models of leadership. You need good ingredients. You need good students, good postdoc, good collaborators. Well, then there is the environment. Well, it's a broader environment, right? And in general, you can, once a group succeeds big time, it's easy to trace back and says, look, this guy who leads it is a well-known scientist. Look, the students are from MIT or Harvard and so forth. That is not an explanation. What we lack is really a theory of a complex system. People have done spin glasses. It's one of the most, they gave a Nobel Prize, one of the most hardest to break, Paris's book, he said he worked almost 10 years on it, And then he wrote a partition function. He wrote it by willfully make a forbidden mathematical step.
Divided by 0.
But he was right. Not so.
Not so outrageous.
In the limits.
Then eventually people came later and, they put it on a rigorous footing and so forth. So, I mean, whereas not, we can do we can do the weather and so forth, but the research, I think, look, if we had a model, scientific model of how
to do good
research, that would be a fantastic things, I mean.
We're trying to get a little bit to the
build
bottom
like
of that by building an
by
archive
talking
of
to
these
scientists like
interviews,
you
like
and
the
others
No,
to-
I mean, but this form is more, can we make an actual model? More than to say to fill in all the ingredients are obvious, right? I mean, if you don't have the ingredients, the likelihood that it happens is always
Yes.
luck.
Yes.
It's not, but right, the path of discovery, and that's why I completely agree when a social scientist claim that the social context matter, and the physicists that say this is all bullshit and so forth, they are wrong. I mean,
Yes.
if you use it in a crass way, yes. But right? I mean, why certain discoveries, happen in a particular place and a particular time. That's why I think we need a model of research, and was written very prominently on it is my former dean and the lab director at Harvard, Venki Narayanamurthy. Okay, he's written once topic, I think is the nature and nurture of research. He's written some very quite deep things on it. What we need now is an actual model.
But would Bell Labs be like that kind of model? Because a lot of people
Yes,
who
it
we
is,
interviewed,
yes,
a
it
lot
is.
of them are from Bell Labs.
I think so. Yes, that is a good that's all qualitative. I'm talking. Can one make a quantitative model of discovery of research?
from like studying the
studying,
model of Bell
what I mean,
Labs,
right?
which worked super well,
Bell Labs was a unique. It was the fact people had a lot of freedom, but at the same time they were evaluated every year, but then still decision about keeping or not people were not made by looking at 1 year. They were making, it was sort of like a sliding thing of 4 or 5 years. Over 5 years you could judge typically. There are exceptions, of course. Right, and I know some pretty important cases of people that we let them do what they wanted for quite a long time, and eventually the breakthrough came because there was the confidence that was a scientist working, on top. In the past, this could happen in universities. It's not happening anymore. I mean, I remember when K.G. Wilson won the Nobel Prize for phase transition, okay? They interviewed after that Hans Bethe, who was at Cornell, and he said, people were starting to ask, is this guy going to publish something? Because eventually he needs to get tenure. But then there was Hans Bethe who said, look, he's working on a tremendous important problem.
Yes.
If he gets it, he might win even a Nobel Prize. And that's exactly what happened.
Yes.
So now this is not possible anymore. It's very hard. I mean, it's very hard.
So because of the funding structure?
No, it's and also the pressure, and also the pressure, because at the end of the day, people are going to ask, a bit of counting papers. I still think in the top physics department in the US, this is still possible, but it's not as it was in the past. Again, research is becoming too crowded, right? So.
But how come there is no private sector Bell Labs, and what about large companies with lots of resources?
Well, I think now,
Amazon,
yes,
Google,
that is a very
Meta.
difficult, very
Yeah.
interesting question. That is a very different model right now. There are all in a sense, some superficial similarities, yes. The good thing, because we have extraordinary rich companies, they've started some long-term research. That's a good development. Look at Google, even in quantum computing. I take my hat off, It's a detail, whether they have achieved, this famous break-even or whatever. There is a technical name for it. It doesn't...
Supremacy?
Supremacy, I mean, this is a silly controversy. The fact is they're doing very good work, Google. No one can question that, right? So there is also Amazon, right? Right. In fact, Oscar Painter is there, right?
Yes.
So this is a valuable thing. I think quantum computing, maybe a lot of the breakthrough, maybe a lot of it will come from industry. So this is a good development in selective areas. I mean, we don't have anymore, and I don't think we can. The system, right, cannot afford it. Bell Labs was a unique thing. There was a company, there was a monopoly. AT&T had a monopoly on phones, communications, right? As a result of it, it had to give out its technology. In fact, when a transistor was invented, Bell Labs publicized with a lot of public lectures, that were open to industry, to anyone. Okay, so that was a model because there was a monopoly. When the monopoly was declared, was thrown out by a judge, Judge Green, I don't...
Is that when the stock fell 97%?
No. I mean, it continued still for a while. That was in the early 80s.
Yes.
I think it continued till I was there till 2003. I would say till 2005, even 10, and it continues to get Nobel Prizes. Bell Labs. It's amazing. It has gotten since I left 4 or 5 Nobel Prizes. Important stuff, including chemistry.
Yes.
2 in chemistry. I mean, it's amazing the stuff. The stuff that in the pipeline takes a long time to give its fruits and to be recognized, right? But I think because this model is centralized model of monopoly cannot exist anymore right now. So in that sense, even though it was a great thing for society, it's not possible. But some of these companies, I think, are going to do a lot of good stuff, right?
I guess there's like a quasi-monopoly or...
Well, yes.
Or at least the winners who would take most of the market.
You're right. I mean, I'm sure there's going to be lawsuits because they're always, when you get so... In fact, Google has already been sued, I think, for monopolistic practices, right?
Yes.
Especially I have actually no problem for that, to get that you have... look, research costs a lot, so for them, it's basically pocket change.
Yes.
But if they have smart managers that see the actual potential for it, why not? I mean, Google is getting a lot of it. Certainly a lot of PR.
Yes.
Right? A lot of nature, sciences, It's good. PR is good for science. A lot of people are going to Google, right? And also Amazon and now Meta.
Yeah.
And they pay salaries that... These companies pay, including Apple, starting salaries more than $300,000. You understand that?
Very attractive for the students.
Yeah, sure. Right? They have made it, right? Even if it's only 5 years, right? They pocket 300,000. They don't have a family often, right?
Yeah, well, usually like 26,
I mean,
27.
What I've told some of them is this. It's okay to make good money, but if the main motivation is not science, is to make an impact, either in science or technology or both, you are in the wrong place and it's going to distort your thing. I remember once Venki told me something I found very inspiring. He said it, he says it applies to himself. If I told me here at Harvard, see, Federico, I've always kept a small research effort, 2 or 3 students, even at Harvard, he had grants. Why? Because he said, I think that I need to, it's important, particularly for a scientist, to be faithful to your vocation, faithful to your vocation. So I think the students that go in a place is primarily motivated by the money, and then, or the next step, because then there's always a next step. They're going to offer you maybe 500,000. They're really not faithful to their vocation. In the future, they're going to regret it, because it's like it's like
Down spiral.
It changes the incentive.
It's like something even more personal. You think you found the right person, you fall in love, and for whatever reason, you don't pursue it. You're going to get some regrets, most likely. It's a bit. It's a personal thing like this. If you have a vocation, if you have the drive, if you have the call, and you don't answer the call because you are distracted by an enormous salary, that is the risk of paying people so much early, right?
I feel like Apple is not following the motto of Steve Jobs: "Stay hungry, stay foolish."
Yes, right.
And in the past, it used to be hedge funds. Like they used to suck off so many
Still,
things.
I'm sure still.
Oh,
Suck
yes,
out,
when I
like,
went to the
so many
Metalenses, this when it was
theorists
the
from
Wall
the-
Street, when Wall Street was hiring physicists by the droves,
Yes.
for quantitative stuff,
Yes.
But they were offering salaries that were typically twice or 3 times what a tenure track would guess. Guess what happened? People, in fact, left the lab, some very talented people. I think they got lost. Right, so that's what I always tell students. Of course, you have to cultivate your own passion, right?
Yes.
That's not easy. You have to keep always...
I had the same temptations. They would call me as well. And I would tell them, I don't know how to do finances. Like, doesn't matter.
Yeah.
If you have math,
they like to
physics,
come to
you
campus.
pay a price.
Yeah. Yes.
Not always,
Yeah.
You also need people like that, obviously.
So you started from, your first papers were based on plasmonics.
Yeah.
But I feel like at the same time, there was also maybe like in the shadow part, there's kind of a dielectric,
this was
nanophotonics.
No, that was absolutely right. I mean, at some point when this paper came out, the nanoletters, I remember clearly, and I had Reza, fortunately, in my group, I said, Reza, it's important that you do a dielectric metalens. That will have a much greater impact. Also because the foundries are not going to make plasmonic lenses. That's a fact. It's not that they can't do it.
Gold
They're just
diffusers.
I even
Crazy.
underlined the line there. There was like a statement, the present limit of our design is the focus and efficiency approximately 1%.
Exactly right. So that was part of it, right?
Yeah.
Right. So, yeah, the technology, I mean, these things you see appear to be simple, and they are in a sense, but often it's decisions like this based on pragmatic. I'm always think of myself, I'm one foot in ideas and an idealist, but the other side, I'm very pragmatic. I want to make an impact. I'm still very ambitious. I want to make an impact in the real world. So sometimes the decision is simple, right? If you know that the chip makers are not going to tell them to put
Gold in.
gold.
They will be so upset.
Right? Exactly right.
The diffusers everywhere.
Yeah, in fact, some of this,
But for dielectric, like for people who worked on dielectric structures,
yeah.
why did they like overlook that area, or was there like some other work?
Maybe a
No,
different.
because it's interesting. This is something like a convergence that happens, I actually wrote a paper on Optics Express that in the title we put, they're making metalenses with Alan Shee, first author. Essentially we talked specifically about, there is a whole part of the paper on why this is the way to go with manufacturing. Because this was the first paper that we use. See, the methods are the following. One is eye-line lithography. Eye-line lithography is not deep UV. It's not widely used, but uses commercial fab lines, So we did this initial Metalens with RNC with eyeline lithography, but then after we made the one class Metalens with deep UV lithography.
The ping pong paddle.
Yeah, that was one of my favorites.
Yes, and that one
the
really, and
sun eclipse. And
But also, maybe a different way to put the question is, what would have been the earliest time where a metalens, a TiO2 metalens, could have been realized, and why do you think it hadn't been done then? Like, what was the spark that
I think
pushed
the
this?
ability to do, say, this combination, this process that was designed by Rob Devlin of casing, of using a combination of ALD and E-beam lithography. So he could get really extremely well designed nanostructure. And then Reza, the next step, Reza made the Metalens. In some sense was an obvious step, right? It was this particular high precision. Now, keep in mind that the technology that we use, it's not E-beam lithography that is used for mass manufacturing, right? But that for me was the next step. I said, now we have to, and we had to, this stuff here, right? Right? And then last year, this is now, no, there was a previous one.
Yeah, there
Nanoletters.
was. Yes, there was another one with
Nanoletters,
like
Okay, I don't think
which is a 1 centimeter.
with the 1 centimeter lenses,
Yes, 1
yeah,
centimeter.
with the lots of small ones.
And here actually stuff, the good thing here, I had
Yeah, those were done at
a
Cornell.
great.
where are the limits? So this is the current record for number of
look.
metaatoms? What is it, like 20 billion?
Look, the fact is qualitative things speak by themselves. Here we didn't put the eclipse because we put it
Yes, I
in
saw
SI later because of the publication, but we saw a beautiful eclipse,
Yeah.
So where did the inspiration come from? Like this poetic, showing the eclipse
No,
with the
because
with the
I had
metalens?
a student who
Arman.
participated.
Arman, he
exactly.
loved astrophotography. He
Yes,
would
and
drag
he
everyone on it.
jumped in it, and the day of the total eclipse, he was up in
8th of
Vermont.
April. Yeah.
with a 10 centimeter metalens, with a filter, of course, with a filter around the actual red, okay, where he really wanted to get beautiful pictures. So he knew exactly what needed to be done. He timed it with this publication. It was great. It was really, Arman was kind of
The right person at the right time.
an unmanageable student.
But a very passionate astrophotographer.
Yes, completely unmanageable.
And that metal lens is at 632 nanometer.
Yes. So
It's a helium-neon
our podcast
wavelength.
is called 632 nanometers because of the Heaney laser.
Oh, I see.
Yes, because it's red.
Why did it start? Why did you put that wavelength still and not the CO2?
Oh, you have favorites?
No, I'm asking.
10.6, 10.6.
Well, you could use a ruby laser also, but I
Ruby, yes,
understand
ruby is a bit, yeah.
because it's so widely used.
Yeah, I think it's a bit more recognizable, although people still ask us all the time. Like,
What are the most used laser these days? Is it
CO2 for manufacturing?
in the
Yeah.
Well, there's a
64?
semiconductor laser is by far this again is a large scale impact, until the semiconductor laser came, and particularly the double heterostructural laser for
This
which
all gas?
Alfirov won the Nobel Prize. Until that laser had a huge impact on telecommunication. Without that laser, we couldn't have telecom. So it's a semiconductor laser used for communication application that now are at 1.3 or 1.55 micron. That is by far the most widely used laser. It dwarfs everything else.
Yes.
So are this the VXL to connect
The VXLs also, but I'm not familiar. It has definitely. Look, I think you are right. The VXL is also widely used. It's also it uses the same principle of the double heterostructure in terms of how to generate lights.
And then just the cavities.
But it is the cavity is different, right? But it's definitely another good example. But then again, the limit of the quantum cascade laser is, of course, the physics is fun. It has an application for sensor, but no one has found yet a killer application. It's not because of the QCL, it's because the mid-IR.
Yes.
The mid-IR, it's a niche compared to other wavelength ranges. Yes, it's used for sensing. Yes, for imaging, and particularly these infrared cameras at night, security. But if you talk of the size of the mid-IR market compared to the near IR and the visible, it's much smaller. And that cannot be changed. Maybe in the future something else will come, right?
Yeah, but I feel like good detectors are.
Yeah, part of it is good detectors. Yeah. She's right. Detectors need to be cooled. Okay, particularly for long wavelengths, right? So that's definitely a part of it.
With your most recent paper, you moved to quantum applications.
Oh yeah, we can talk about it. In fact, if you move over to the slides there, see it was mounted to look at the eclipse. The next one, not this one. Next one, that's the eclipse. Wow. And he could see even a solar prominence. You see, it's like plasmas that is emitted.
That's amazing.
Yeah. No, they are beautiful. These are state of the art. Because it is a Metalens.
Yeah, it is.
I see a lot of masterpieces in your research happening. Oh, it's either capturing these details with the new technologies or the beautiful formulas.
We can continue.
Continue
for the quantum one.
Yeah, the optics with mass manufacturing. You see, this is a 12-inch wafer. In this case, it's actually glass, but it's the standard is 12-inch, right? So now people can make 12-inch things with amorphous silicon and make the metalenses, right?
How expensive would that whole wafer be? Insanely expensive.
I guess it depends on the quantity.
It depends on volumes.
Yeah.
But the whole idea is to kill the price.
Economy of
scale. Kill the price of the metalens. I mean, ideally you would want them to cost less than an actual dime.
Yeah.
Right, because it adds weight but adds cost. And for mass market, this is our things that I learned also. For mass market, difference of pennies make a big difference.
Oh yeah, absolutely. Yes.
Right?
Yes.
And we find it's interesting. Once I remember I looked at the cost of a transistor to fabricate a transistor is basically zero. It's a millions of an actual penny. You take a chip with a billion things like billion gates, which we have in the phone. The cost is zero. So you tell when I tell this to the students in the course, they are puzzled.
So that should be the Moore's law, the price of the transistor.
Yes, that's exactly right. It's fascinating. Now, meta-optics is not quite there, but it's an interesting question. The size, we don't have to go as small. And, if in fact it's interesting, we are using the same technology of chips. But, chips, the resolution, I mean, the tolerances are very tight. They are nanometer. And the reason being that what matters for chips is the de Broglie wavelength for the electrons.
Yeah.
Whereas for meta-optics is the wavelengths of light. So the tolerances are much more forgiving.
Yes.
That's how I explain it to people. That's why physics understanding is important. That's exactly the point.
Yes.
Right? You don't worry about... We had the variations in the titanium dioptics easily 20, 30 nanometers, no problem. The optics doesn't see it.
Yeah.
It's still diffraction limited, right?
Yeah,
cool.
even when
we
still had it embedded in the resist, you could already test it, and it would be diffraction limited. It would be less efficient, but it was still do a nice job. Yeah.
Yeah, the efficiency is still a problem
Yeah.
to be solved. In fact, we have a lot of effort in my group when working with a couple of companies, Samsung, KLA, and others, where the big thing is also with Corning is, and for that we are doing a lot of sophisticated type of design, inverse design, and so forth. You know, it's sort of it's interesting. It's the next set of problems. Let's move. I want to show you the
Is this
quantum.
amorphous silicon on this 12-inch wafer?
Yes.
Yeah.
Another thing I realized when working with meta optics is that the complexity of computations, while you start to increase the size. So, I mean, also I was looking into, like, for example, this paper, the way, I guess, like, you have
you can
20 billions of geometries.
Yeah.
That's a lot of
Yes.
computation.
By computation, this is easy because it is a lens.
Right, but if, for the arbitrary control of the phase, how, like, when you don't have symmetries and
Yeah, but this what the beauty of this is we have the radial symmetry, okay, in the lens. So once you have an actual line, you have the design of the whole lens because it's rotation invariant, rigorously rotation invariant. So you just simulate a line, and then you just rotate.
yeah, with the lens that works perfectly.
Yes,
but
exactly.
for arbitrary cases,
Oh
of
yeah,
the
it's
phase
that's
map.
why design is. That's where the frontier is now. People are doing. In fact, we are doing a lot of inverse design, right? And we're going to get big time into AI. You know, machine learning. I have one student. She's very brilliant. Pernille. She's Norwegian, and she's doing a great job in learning these techniques, machine learning and AI. I tell you, this is fact that people need to learn.
Yes.
But even just, I would say, in my cases, I would have to use, like, one of the, for the largest meta surfaces, like one of the, like, top servers available. So this is, like, thanks to the technology. Like, if it was, like, back in 90s, there would be, like, no way to just save that information.
I think that the technology here is definitely, the hardware technology is advanced to do practically anything more easily than you make chips, for sure. Right? The interesting stuff is the bilayer metasurfaces, which we have done last year, a paper which is getting a lot of attention, because there you can overcome some of the limits of single layer metasurfaces. Okay, and then it gets very, very interesting. For example, structure that are illuminated one way behave in a certain way, and in the opposite way, in one way you have a lens, and in the other something else.
Yeah.
This is
basically you have
fascinating.
a bi-anisotropic material.
Exactly right. Let's
here
see.
we
This is,
have
I mean, you know some of the stuff. This is linear quantum optics. Okay, if you use typical, beam splitter mirrors and so forth.
That's the photonic supremacy experiment, right?
Yes, but you know what I mean.
Yes.
That's why. That's why.
Yeah.
So the motivation of this work was again ultimately technological. Okay, so these are the challenges. So if you go to the next. So now this is stuff. So we went back to the basic, and this is the famous Ongu-Mandel type of experiment. If you send two identical photons into the ports of that, okay, what you find that they both come out in either the port 1 or port 2. So the quantum correlation are such that the terms where one photon goes out in one output and the other at the output cancel out. Okay? And it's the bosonic nature of light, but it's a fundamental experiment. I would claim it's as foundational for quantum optics as the Young experiment is foundational for classical optics,
The double slit.
Finally getting the attention, and you can do it, you see, both you can do it both ways. You can have the two photons coming from two different spatial modes. Okay, so it's there. Okay, or you can have them essentially come from states of horizontal and vertical polarization. Okay, but you still get this effect. Okay, that you get the two vertical photons in one port and the two horizontal in one, and the mixed thing cancel out. It's kind of it's really fantastic how quantum mechanics work. You know, this is a fantastic example of a entangled state. It's an entangled state of two photons.
Yeah.
You may think. I think the more I created a course in quantum mechanics, and the things that I said, both the Stern-Gerlach experiment and then the entanglement is something that really has absolutely no classical analog. And in fact, I think entanglement is so profound, the fact that you can you create these photon pairs, one goes one way and the correlation persists for the distance of the universe and so forth. So I actually...
Well, we didn't check it yet.
No, we
There
didn't
is some
check it
loophole.
yet, but I actually think that there's something deeper in entanglement. I have no way to tackle it because I'm not a theorist. I think it requires some new concept of space-time. Basically, we have not said the final word yet on the space-time. They're the type of nonlinear correlation somehow. I think the structure of space-time has to be reconsidered, in my opinion, because there's something extremely weird is happening. And just saying that the math,
Yes.
there is absolutely no intuitive understanding of entanglement. In fact, you throw your hands up and say, this is nonsense, right? Then you do the experiment, for a limited distance, and you are right, because someone could still say, why there is no cutoff for entanglement, why there is not a distance. People have tried to introduce a cutoff, but they haven't succeeded, right?
I think the highest one is maybe Jiang Wei-Pan. Did he do the satellite one?
Yes, exactly. So, and also, first one, it was one in Geneva with the fibers, right? But then there is one of Pan, right?
Yeah, it's pretty crazy.
So let's go. So the idea there was, that was exactly it. I said we are now using the diffraction orders as part of interferometers. That's a simple idea. So you see, we can engineer. These diffraction orders now we can decide the correlation. For example, between certain pairs, we have correlation. So we have a Hong-Mandel dip, okay, for photons coming out in those pairs. But for another, we have an anti-Hong-Mandel, an anti-correlation, an actual peak.
Yes.
And that was the guiding idea. And, Carlos is a fantastic student. I mean, we submitted this paper to Science. We were very worried that they would shut it down, but the reviewers were fantastic. They said, this is one of the most rigorous paper we have seen in the field. Everything is explained so clearly. And, so I was very happy.
Yes.
So we can go to the next. Well, that's what it is. Okay, so the math gets a bit complicated. So at the end, what describes this correlation is this so-called Herbert-Schmidt product. Okay, which what you do is you basically this is another case we have to use this matrix Fourier optics, okay? So we look at the far field. See these detectors here, the orders of diffraction. This is the power of this matrix Fourier optics. That the Fourier, the Jones, the Fourier transform of Jones matrices in the far field can act as analyzers, as real physical analyzers. You see, as if you had an analyzer there.
Yeah.
That's when we did this stuff. And that's really conceptually novel, that it's a way to, it's an abstract way to look at polarization that people initially had trouble, and understanding, but then you work out the math and then you see the experiments, and then the most things are revealed is when we had the Metalens camera, we had to, polarization camera, we had designed 4 diffraction orders, which they analyze light of 4 different polarizations, because you have 4 Stokes parameters, basically. Okay, so they acted really as polarizers, for example, for elliptical polarization. So if we illuminated the scene, the metasurface, with elliptically polarized this way, you would get maximum intensity on that diffraction order, designed as an analyzer for elliptical polarization. Then if we turn the ellipsis 90 degrees, the intensity would go to a minimum, malus law.
Yep.
So we showed that in that paper, and that was really clinched it. So the abstract notion that the diffraction order can act as an analyzer. It's no more the bulk component, right? It is, you have the function of the analyzer in the
It's like ellipsometry, essentially.
Yes, but it's done getting rid of all the hardware.
Right. Simple,
Yes.
compact ellipsometry.
Because normally you have to rotate.
Yes,
Two analyzers.
Like-
exactly right, exactly. So there, the next thing there is, this was the initial experiment we did, on a simple, with 2 diffraction orders, right, to look at the correlation, again, coming in with horizontal and vertically polarized photons.
How do you generate that photon pair?
The SBC.
Here by this, it's called
BBO.
this parametric down converter,
Yeah.
right? And then they're polarized.
Are they identical in wavelength as well? Or
Yes, they're identical in wavelength. This is degenerate.
Yeah.
Okay,
So
but then
indistinguishable.
you polarize them differently. Well, you see, then here this is the design of this diffraction order, okay, which actually, it's very interesting. One analyzes for diagonal and one for anti-diagonal light. Okay, so polarize 45 degrees, and then 135 degrees, right? But that's just an example, okay? So what happens is this, okay, because of if you have 2 diffraction orders, you can get always rigorously a natural dip, okay, because of conservation of probability. But when you are with 3 diffraction orders between the actual pairs, there is always some leakage of light in the other orders, right? So you have to optimize that dip, okay? That's kind of natural, right? So that one, that shows the home interference. That's still the 2 photons, right? The 2 ports.
The correlation degree. Okay.
Yes. Then let's go to the next. Now this is adding one more diffraction order, and that's gets very interesting, because now what happens is between the red and the green port, that's a way to label, you get the ordinary correlation, okay, basically that you get a dip, okay, right? The photons can come out either 2 out of the green or 2 out of the red, okay? But in the green, actually, they're anti-correlated. If you look at 2 diffraction orders, you will find an anti-ohm peak.
That's pretty cool.
It's pretty cool, right?
Because you can.
It's very nice.
Because people had calculated that using fake beam splitters to
Yes, right.
do that. But yeah, this is pretty nice.
So I think this is, I presented this at this meeting of European and American scientists working in quantum, and I presented this, and yes, I think it got quite a bit of attention. I mean, it will take time to sink in, I think
because you're thinking very differently.
Yeah.
Previously, it's like sequentially on a chip. Now it's like in parallel. Yeah.
Next. See,
That was the anticoalescence. Yeah.
on between the two green ports, you get an anti-ohm. It's still a quantum correlation, but that's why I think what attracted me initially is the idea is to design in an arbitrary way the correlation between diffraction orders. So you can engineer pretty strange things. Whether they're useful, it's another story.
But it is another parameter to play
Yes,
with.
exactly.
Yes.
Yeah.
Yes.
This is a very nice contribution of Kerolos. He studied some graph theory, and you can write down these interferometers. These are interferometers as actual graphs. So it's fascinating. You can draw a graph, okay, and then ask yourself, how do I implement it? What is the metasurface, you see? So there is this dual point of view. Once you've done something, you can definitely write a graph. But then you can say, now I'm designing on paper something like this. What does it correspond to? It's very interesting.
That's very creative.
Yes. Yeah, Keros is a very creative guy.
Now we try to expand into larger modes.
Yes, I'll show you. I'll show you in a moment. Yeah, for example, this is this is the Hadamard interferometer. It's foundational, okay? And typically, and the way, if you had to do it with mirrors, it gets and beam splitters. This shows how you would do it with beam splitters. Look, you want to have more outputs. Look at the mess, right? It goes to 2 to the n, right? The number of components, right? Whereas for a metasurface, you can, using these graphs, you can actually design the same functionality by staying simply on the actual surface, right?
I guess fair question to ask is what's the efficiencies in comparison to?
Well, the efficiency is still one has to. You will see. This is a question. What is the visibility of the fringes? And we'll show you the data in a moment.
It reminds me some of the what's called boson sampling.
Yes, there is a relationship to boson sampling. So here we studied, for example, the polarization of metasurface with 4 diffraction orders, where those are the data there. The arrows on the Poincaré sphere are both the actual target Stokes vector and the measured Stokes vector. So what Kerolos did is a Stokes polarimetry. We've now becoming very expert on doing Stokes polarimetry. Stokes parameter is an interesting story. When Stokes came out of this, it's a fascinating story. When Stokes came out describing polarizations with intensities, people largely they didn't understand what he was doing. And what I read about it is what is so exciting and fundamental is that it's the first time in physics that a fundamental quantity was defined through a series of measurement, because that's what the Stokes parameters are. It says, if I take polarizer oriented vertically, I measure the intensity, then horizontally I measure the intensity, then I do it for this 45 and this, and then I take a circular polarizer this way and I measure it, and from these 6 different measurements, okay, I can derive the state of polarization. People thought he had no traction whatsoever. And what I read later, only with quantum mechanics, later it became, this is the first time, certainly in classical physics, ever, that someone defined a fundamental physical quantity with a set of measurements, which then became standard in quantum mechanics, right? You can define only the spin in a sense if you do a Stern-Gerlach experiment, right? So it's very, that's why it's also, I find, for students intuitively hard to swallow that polarization can be defined by simply intensity measurements.
Yeah, it is weird.
It is weird, right?
Yes.
Stokes was a genius. I mean, what this guy did, you know, if I went once to for the celebration, they invited me for the celebration of the 150 years of Maxwell's equation. They organized a meeting at the Royal Society. And then we looked at they exposed the manuscripts, the original manuscript of Maxwell's equation, you know, which was not written the modern way with the curl and this, but it was written with 18 different equations, differential equation, and NES.
Yes.
And the editor of the Proceeding of the Royal Society sends the paper, no, Stokes, who is the editor, sends the paper to Lord Rayleigh. Okay, so it's the correspondence. Then it sounds very modern. 2 months later is not an answer, so so Stokes writes to Rayleigh, he says, you know, can you accelerate the reviewing? So he feels very pressured. He says, I apologize. I'm not going to forget it. You're going to get it within the next few days. So sounds very modern.
Except with like horse carriages and mail involved.
Exactly right. So the next... well, you see, in this you can see, for example, for the 2 ports, okay, we are doing pretty well, okay. You can see the green line is the classical thing, right? So we can do it. We are doing okay. I think we can say we can also do the 4 orders, but we still have much better to do in terms of the visibility. You see, that dip is not as pronounced as it could be. So that so far it's a limit, and I think it relates in partly, it's related to the efficiency. So the total probability needs to be conserved, but it's simply impossible to design things so that the dip is not going to be affected by the other orders. There is always some light diffracted on the other orders, so that dip will never be as deep as you would like it. Right. So the question is,
as it gets.
Yes.
Yeah. But if it's under 0.5, I guess it depends on the threshold.
This is one of the things that draw some critical comments, but at the end they accepted it because we said we were honest. I mean, I think there is still some improvement possibly.
Can you combine the generation and the interference in the metasurface, like use an SBDC material? And
that would be very interesting.
That would be very cool.
Absolutely right. And this relates actually to an interesting question that so far the work done on nonlinear metasurfaces has been, in my opinion, of limited interest. It's been mostly in the mid-IR, using inter-subband transition and so forth. It's cool stuff by Misha Belkin.
Yeah, in terms of like taming the phase, and then which corresponds to 2 polarization states. So we have like, let's say, pixels, and then for each pixel we can vary its size, and then assigns its response to polarization. Then the question comes, how small can be these pixels, or they need to be smaller than, unless we suppress all the other orders, and then how abrupt could be changes in phase, because that could lead, we didn't discuss that much, like on the micro scale, how these antennas behave, and how these effects of intercoupling. And
that would come interestingly. This is something that we have started to look at. You see, the modeling has a big oversimplification that has served us well, but now we are looking at the limits. We are assuming, when we calculate the stuff, we are assuming periodic boundary condition. Basically, that the unit cell is surrounded by identical unit cell. That's a fiction,
That's
which
right.
works in many cases where the variations are not too steep, right? But let's say, for example, where you have to really start to have extremely tight focusing, okay? Then there you start to have to worry about, coupling between elements, and then it gets actually very interesting. Okay, you can use the coupling as a natural design. For example, in the direction of, if you try to focus, the more tighter you focus, and this also happens, in fact, if you come in at an angle, okay, you get an efficiency drop. Okay, so that is a situation in which we wrote a paper on supercells, okay, where you want to take into account the coupling to the nearby, maybe the whatever number you choose, first neighbors, next nearest neighbors, and so forth. Define a U-unit cell and use that for computation. That is a way to relax the constraint on efficiency and cure, in part, the efficiency problem. Okay, and it's actually very, very interesting, okay? I mean, we have a paper recently which just came out in Nanoletters on the notion that says, that it's better to use, to have a large contrast of a refractive index, okay, which is true. It helps in a number of cases, but there we have shown, in a simple example of a lens made, I think it's made of glass, okay, where, the refractive index is, the contrast of the refractive index is very small, right?
Yeah,
What is it, glass?
0.47.
Probably, and then the air is 1, right? Yeah. And that there is an interesting thing that you can, you see, one thing that you need to be careful is this: the modes of the actual pillars. If you have a pillars that sustains more than one transverse mode, okay, then these transverse modes can actually couple and form block modes. So there what we show is a beautiful picture. I love it because it says, it gives the story out completely like that. That the wavefront, now if you hit it with a wavefront and you have to couple to more than one transverse mode, the wavefront is actually messed up a bit from the planarity. Whereas if you design it as a pillar, a strictly single mode, you get a much better wavefront. So it's an example where you can use, the low contrast of refractive index actually to your advantage, right? And this is something that had escaped the attention of everyone so far.
Very interesting.
In fact,
very counterintuitive.
In fact, we put it in the actual title. I say we made it's like a statement, the title that says, situations in which having a low refractive index contrast helps for the creation of the wavefront.
Yes.
Yeah, it had escaped us completely.
Because normally you would like to have as high contrast as possible for
this
confinement.
Is a spirit of observation of Luca.
Very nice.
Yes, it's his last
Yes.
paper, right?
Ah, very nice.
Yeah, he came up, and it's interesting. The actual thing is, he was expecting to see a very good diffraction, sort of standard, like we were talking at the very beginning, right? What are these ripples? And then, his mind started to turn, made some calculations, says it is the transverse mode, where I'm exciting more than one transverse mode, that messes up the intuitively the wavefront.
Yeah.
Right, because the diffraction is different if you have one mode or two, right? And he calculated, and then it's exactly how the experiment behaves, and then cleaned it up by having a structure single mode. It's beautiful. I mean, again, it's an example of my favorite story is this, right? That I can tell a simple story. Of course, there's still a lot of hard work, but
yes.
So maybe it's like some kind of conclusion. What would you tell to maybe like younger generations of
well, I think
scientists?
I say, because every year when new graduate student come in the School of Engineering, they ask me to be part of a small, call it a panel of 3 professors,
Committee member.
to take questions.
Question, I see.
Questions from new students, So the question always comes, One question that comes always, and I'll tell you how the answer that I give is the work-life balance, which is a good one. And what I tell them is the following. Look, basically is that if getting the PhD is not your most important goal in the next 4 to 5 years, this is wrong. Okay? You still can find time to have friends, boyfriends, girlfriends, have fun, whatever, BS. There's nothing that prohibits this. But just keep in mind that if you don't, it's not the number of hours. If it's not the main, and I tell it needs a certain single-mindedness. It means you can't be in a situation that you go home and forget about it. I mean, this is not realistic. Right? The problem follows you. Of course, if you had small kids, like with my wife when we had the small kids, it was hard for me. I remember, and I tell the staff because I want to tell them that you have to make, it's still important. It took me 6 years to learn when I arrived home to forget the work at Bell Labs, because you become passionate about it, and the students should operate mentally in this mode. No one should measure the number of hours. I never measured the night. Did you ever ask students, did you come last night? Never once. Never. And I'm proud of it, because it's not the right metric. In fact, it can induce only an exceptional guy, who was Junsu, that would do these crazy hours the whole night, till 3 o'clock in the morning. Then I couldn't. Sometimes I wonder, what is this guy doing? But work was coming out.
Yes.
But that was an exception. And I tell him, in fact, I tend to discourage, if at all possible, I tell him it's much better to work methodically 8 hours a day, right? That's I tell them this balance. But I also say, you need to have a normal life. But keep in mind still, and David Miller also says this, I tell a student, look, if the experiment is always working, you are a fool if you go home, because you work so hard. You leave it for a few hours or for a day. You come back, the effect has disappeared. We know it.
Yes, I concur.
Entropy
You need to be
happens.
superstitious.
Yeah,
stay all night.
Really, it's something. It's just because often you just the balance, right?
Yeah.
And that's why you need. And the other things I tell them, the important thing is actually passion. You have to. I tell them to fall in love. The relationship with research is. It's not just the mind. It is your whole spirit. It is a passion. It's like a love affair. Right? You can't rationalize it. You have to have the drive and then put the work, And I tell them, I downplay the intelligence, because I'm telling you, I think the intelligence plays a role only really at the very highest levels. You know, we are talking of geniuses. I mentioned Fermi, you can mention Dirac. Those I don't even mention these people. These are the exceptions, right? Of course, it's important to have had these people, but we shouldn't be talking about intelligence because often, not grad students are a bit, but the undergraduates, sometimes I've heard, particularly from female students, you know, and that's bad, you know, well, I'm not capable, I'm not intelligent enough, and I just say nonsense. That's not the main fact. Of course, a reasonable intelligence helps. It's mostly the actual passion, and that was my case. I mean, look, I fell in love with physics 6 years old. Did I build motors? Never. Was I good with my hands? Not particularly. Did I had a talent for science? No. But I loved so much to read about whatever I could read, you know, Scientific American, that I always, when I was ready to go, I said, I'm going to be a physicist, and I decided when I was 6 years old. And that's purely passion. Some cases it's actually talent, you know. I know a lot of people that were building motors, doing things, building motors. Feynman said that, but I don't think these are necessarily good examples, you know.
So how did you fall in love with physics? Probably discussed it in the previous episode, but it's good to
Because my dad gave me a book, Our Friend the Atom.
Oh.
Oh.
Okay, I should get the same for my son.
He just had a son
Which was
3.5 weeks ago.
Which is, and I read it. I literally fell in love with it, and I said, I want to be a physicist. It's too much fun.
That's amazing.
So a book made a huge difference for me.
I need to get that for my niece. Yeah.
Yeah, I mean, I think it's important to kindle the passion. You know, we failed with our two daughters. They're doing very well. They went into business, you know, and we did everything we could, leave books around, get them interested, you know. Right? And we didn't even do it too intensely, because if you do it too intense, you can have the opposite effect.
Yes.
For sure. You have the repulsion.
Yes.
Right?
You also mentioned you're not a big fan at all of all this traditional metrics of science. Or how would you, what kind of
Like
metrics
H
can we
index, let's
use
say
in terms
H
of?
index.
Look, H index, I think, drives. I had particularly Oriental students, I must say, but even when it came out, I would get asked sometime when I was sessions much abbreviated, you know, at conference or things with, say, you know, how do you get into nature or science? And I said, that's the wrong metric.
Yes.
And I tell them, you know, I publish in Applied Physics Letter. I made my name for myself with Applied Physics Letters, basically, well before the QCL, because they were well written. I know it, and I spend a lot of time in choosing the right word, you know. Yeah, and that book there, which is online, there is a reference. There are a lot of sort of interviews with people who have worked with me and so forth, and you might take a look at it.
Yeah.
I'll send you the link, or I'll send
yes,
her the
yes.
link. Right? But I think, yes, that's... yeah, you were asking, yes, what... yeah, it's just to... It takes a bit of an art. You see what I mean? I think sort of running a group, it's a bit of an art. You know, it goes back, is there a theory of how research is done? Is equivalent to the question, is a theory for an art? You know, can we write down some theory with programming and so forth, very complex thing, maybe with AI, to say how we can come up with something like the Pietà di Michelangelo, one of my favorite sculpture in St. Peter's in Rome, or a great painting, also modern, like Picasso.
Yes.
You know, like, I mean, that's the same, it's a valid question, right? Just to say it's not random, right? Because we don't get art or great science randomly, right? So what is the machinery? We have it's fascinating. We never even barely lifted the actual veil
Yes.
to see what's under, and that's fascinating, right?
Would you
Yes.
say that it's some sort of like a taste, a feeling, what you
Yes,
get while working with?
Taste, yes. Taste for problems, yes. And there is some who wrote beautifully. In fact, there is a great historian of science who passed from Harvard, Holton, okay, very famous. And in fact, his thing is that you can look at the research of people. People go by themes, there are certain themes that inspire research. For example, in case of Dirac, he used to say it, my equation, I could care less that I discover antimatter. I wanted an equation that was relativistic in variant, but was beautiful. So when he also rederived Klein-Gordon,
Yes.
but hated it, he said, this is bad taste. And so he wanted the linear,
Yes.
right? Linear and in just the first derivatives, right? So beauty was his guidance. Okay, in the case of Fermi was simplicity and practicality, right? And as directly, these are themes, and this is what Holton says. So there are definitely themes in the research, in the way everyone. There are also bad teams,
Yeah.
trying to unnecessarily complicate things, I mean, if one takes an example of a very successful group, I mean, the other one, the great one was the operation that at the Cavendish, the Cavendish has been one of the most successful laboratories, wherein huge strings of Nobel Prizes in physics and in biology, and the key there is there was something magic about the place. Okay, that's where it's not only Watson and Crick, that's the most famous, but there is Max Perutz, Kendall and Perutz, the structure of proteins and so forth,
Josephson also there?
Josephson also in Cambridge.
But he did this work as an undergrad even.
Yeah, I mean, he was, Josephson was kind of a crazy guy,
Yeah.
I mean, who told me a very funny story is this guy, what is the solid state physics, famous textbook by these two guys,
Yes.
Anyway, one of them.
Kittel? Is it Kittel?
No, Kittel. It's a two, Ashcroft and Mermin.
Ashcroft and Mermin, yeah.
Once they invited me to give us, and then I meet Ashcroft, and somehow comes on Josephson. He tells me an anecdote. They invite him at Cornell. He was just either fresh of the Josephson effect or the Nobel Prize, whatever. And it's a small airport, a small plane, and the passengers come out, and Josephson is not there. So I said, this is very strange. So they check first with the thing. He's on the plane, so how is it that he's becoming invisible, half an hour? And then he comes out dragging essentially a box full of mineral water. So he said, well, I need my own mineral water or something even stranger. He wasn't sure that Ithaca being a small place, they would have mineral water. It's some absolutely fantastic thing. And he said, and of course the people, he had a hard time probably getting on the plane and then getting off. They says, what are you doing with this? And Josephson was this kind of guy, And in fact, after he went into parapsychology.
Yeah. Seth
Right,
Lloyd was
the
talking
story.
about that when we interviewed him.
But in some sense, he was a genius because there was a couple of people who came very close to it. Bardeen apparently made a mistake in the mathematics and didn't believe, and and sort of missed it, and a couple of other people were dancing, and certainly P.W. Anderson, who then Anderson and Rowell did the experiment to show the Josephson effect. But yeah, there were some strange characters. I mean, Valence was a guy who walked backwards. He was a famous statistician who walked backwards.
Always.
Yes. One day, eventually, he changed direction.
What happened?
And walked
He got
normal.
scattered.
Yeah, there was a mirror. There was he hit R is equal to 1 surface.
Yeah, I mean, there were a number of very strange people. But again, I think this is more the mistake. I don't think there were also so many absolutely normal people. I think we need to strike down, because it doesn't help the young people getting into science to say that somehow
you have to be
strange and bizarre.
Is a
If
prerequisite.
we overemphasize creativity and originality, right, then we downplay the stuff that the three of us know, right, matters most. It's not this stuff. But at the highest level, yes.
Yeah.
I think the Josephson thing,
Yes.
the real big stuff,
Yes.
often there is a stroke of genius somewhere. But for stuff still high level, right, it's not required, right?
It's more like grit and passion.
Yes, exactly right. I think that's more important.
I think that's what also Einstein was saying, that
Yeah.
curiosity was like
Yeah, of
the
course.
main.
And then there's our
Of course, Einstein had a book edited by Freeman Dyson, the quotable Einstein, because he was legendary for quotes. Einstein has so many quotes, but I think his quotes about science are a bit obvious, and coming from someone of his things, they are not very credible. Like he's saying, that most of it he said was hard work and took him 15 years to get general relativity correct. So what? I mean, this is general relativity, and in 15 years it's probably not so much.
That's
right?
actually pretty
So
cool.
he's not credible, right? Right? It's more credible with someone who is good but not at that level.
Yeah. Or maybe I guess Edison is it's 99%, what is it, perspiration,
perspiration,
and
1%
1% inspiration.
Yeah, that's a bit of an exaggeration, but certainly it captures most of the things, right? We know that we've been in the lab, right? That, I remember when the QCL came, it was an act of desperation. They said, after 2.5 years, 3 years, nothing works. So he said, with Jerome, we try one last structure that worked, and I was at the Met. And he calls me during the thing, says, Federico, it lasers.
Jerome Feist.
Yes. I still remember.
That's a good place to receive the news.
But again,
Lost hope.
yes, and often things happen that way, that you just have to sort of, it's like a bull with the horns, and you're going after the wrong door. Right? You're banging against the wall, and the door maybe is just here, and you don't see the door. Right?
Well, on that
Thank you, Federico.
Thank you so much
That
for
was a great
joining us.
conversation.
2nd of January, beginning of the year. It's a good start to the year.
Kickstarting the new year.
Thank you.